Thanks again for joining, everybody. My name is Kevin Wiens. I'm going to run through our presentation for today's topic, which is full solution rejuvenation. Maybe I'll first just get a confirmation from Doug. Are you able to see the presentation on the screen?
I can. Yeah.
I see it fine, Kevin.
Oh, thanks.
Not yet. I'm getting the screen. Thank you.
Okay. It looks like some people are and some people aren't. I'm going to, I wonder if it might be just an issue on your end, Doug, but I'll just get going here.
It's coming through now. Just a little latency.
Oh, excellent. and to give you a little extra time to absorb all the information. So when we're talking about rejuvenation, we got to talk about different alloy types that are out there that constitute the high temperature turbine blade components. And so there's lots of different microstructures that are specific to different alloys. And then the other thing to keep in mind is that those microstructures are changing as a result of high temperature exposure. So every material has its characteristic structure, but then that structure is also changing. And so there's lots of different microstructural states to consider. And so here we're looking at a bunch of different micrographs of different alloys, showing that the precipitate structures vary from one to the other. And for this reason, each alloy is treated differently in terms of how it's manufactured and how it's considered in terms of what degradation has occurred. One thing to note is the two lower micrographs show a change that has occurred within a particular alloy with service exposure. So we're going from a fine precipitate structure to an overaged one with coarsened and agglomerated precipitates. That represents a change not only in the structure of the material, but its properties and the extent of creep that's occurred. And so that has implications on the life of the part, which we'll talk about in the coming slides. So when we look at how the microstructure evolves over time, we can represent that as actual mechanical properties. And so this plot shows how the rupture life of the material, that is its strength, changes as a function of the size of the precipitates. The precipitates start off small and then they grow over time. And initially that's actually advantageous. And so when the part is heat treated at manufacture, we're actually trying to get this initial increase in strength by aging the material to an optimal precipitate size. But as the part continues to age in service, because it's in a high temperature environment, if it's a hot section turbine blade, that strength will slowly degrade over time as those precipitates grow larger and larger. The reason behind this has to do with the way that defects within the material interact with those precipitates and lead to deformation. And so the larger the precipitates are, the bigger the gaps between them, the easier it is for these defects to slip through those precipitates and lead to deformation. If particles are too small, the other thing to consider is that these defects can simply bypass them by cutting through them. And so the way that the precipitates strengthen the material have to do with how they interact with these defects in the material. When we look at how rejuvenation can change the long-term outlook for a component, we need to think about the degradation that's happening with each service interval. So this shows on the vertical axis stress rupture strength of the material, and each and on the horizontal axis we see hours of operation. And so after the first service interval of 24,000 hours, we see a drop in strength. The blue bar goes from around 40 hours of rupture life down to 15. And then if that part goes back into service with a conventional repair that doesn't reset the microstructure, it degrades further down to what we're showing here is about 10 hours of rupture life after 48,000 hours of service. Now, if we instead go and reset the properties by rejuvenating the structure after each service interval, we can remain at a higher strength state after each of these service intervals. So we can go back into service with higher strength. It'll still drop with the additional service, but we get back up there with the application of rejuvenation. And so this allows a part that might otherwise be retired. In this case, this is a component that gets retired after 48,000 hours of service. But with rejuvenation, we can continue its life further. And in this case, when this plot was generated, this set of parts had gone to 96,000 hours. It's since that time exceeded 100,000 hours. Rejuvenation really doesn't have a limit to the extent to which it can be applied. Parts will eventually fall out for other reasons, like say wall thinning or other degradation modes that ultimately lead to retirement. But rejuvenation has allowed for creep at least to be eliminated as a reason for blade retirement. So how we do that is through a series of heat treatments. And so this plot here shows those heat treatments as temperature versus time. And so in order to reset the properties of the material, we have to reset that microstructure. And so those precipitates that have grown and to the point where they're no longer providing optimal strength, we dissolve them by running an initial heat treatment, a solution heat treatment over the gamma prime solvus temperature. And then we regrow those precipitates through a series of aging cycles. And there's typically, for most advanced nickel-based superalloys, there's typically multiple aging cycles. They grow multiple precipitate sizes within the structure in order to get an optimal set of mechanical properties. And so that basically gets you back to that original state because we've dissolved those overaged particles and regrown them back to their original size. They'll continue to grow as they go back into operation, but if we apply rejuvenation at appropriate intervals, we can make sure that the strength is maintained and the part life can continue. Conventional repairs often just use the aging cycles alone. They don't go up to the solution temperature, and so that doesn't restore the precipitate structure. And we'll see some examples of what that looks like microstructurally here. So the top two micrographs, the one on the left shows an initial state of a microstructure. With operation, those precipitates grow, they coalesce into an overage structure. And then when we apply a conventional repair, which goes down to the lower right image, shows basically no change in that structure because we haven't dissolved and regrown those precipitates. But if we rejuvenate, we get back to the original state by dissolution and re-aging of the structure. Another key component of the full solution rejuvenation process is hot isostatic pressing. So this is it's a heat treatment that also involves high pressures, and that allows for collapsing of any internal voids in the material. This is sometimes done at manufacture, actually, as a means for consolidating casting porosity. But what it also does, which is important for service run components, is it can also collapse creep voids that have developed in the material. So that's one of the outcomes of high temperature exposure at high stress is not only the overaging of the structure, but the formation of internal cavities in the part. And so the hot isostatic press consolidates that and truly allows you to get back to the original state of the material. So this shows a couple of other microstructural impacts here. So we talked about precipitate reformation, which we can see in the upper micrographs. And the lower micrographs, we can also see a reestablishment of the grain boundary microstructure. So the image on the left shows an overaged grain boundary. You get actual gamma prime film formation along those grain boundaries, and that can actually have an impact on rupture life and ductility, and the full solution rejuvenation also restores those grain boundaries. We also see that it can address other microstructural deficiencies. So over time, you can get phase formation that's detrimental to mechanical properties. So this image on the upper left shows sigma phase formation within the material. Sigma phase does a couple of things. It robs the matrix of the alloy of refractory elements, which is part of what strengthens the material. It also provides favorable crack growth features, as these needle-like brittle phases can aid in crack propagation, and so these can be dissolved through the full solution rejuvenation process. Now, because they're a function of the alloy chemistry and the temperature of operation, these phases will reform again. But again, just like precipitate overaging, if rejuvenation is applied at appropriate intervals, you can keep the strength up and extend the life of the component. It shows a specific example of a turbine component and its effects from service and rejuvenation. So this shows some overaging of the precipitates, some successful reformation of those precipitates after the heat treatments. And when we actually keep an eye on the creep life of the component, we extract samples from representative blades from the set in order to keep an eye on some of these changes, figure out appropriate rejuvenation schedules. And so metallurgical analysis is a key component of a successful rejuvenation program. So this shows some property changes over time for a specific component, a frame 7 FA bucket made of cast of GTD 111 DS material. So it shows an initial drop in rupture strength and then re-establishment of that strength through rejuvenation. So over time, Liburdi's applied a number of developed a number of rejuvenation programs for different alloys, and they can be applied to various components of those alloys. So it's really not something that's limited by alloy, and lots of different rejuvenation programs have been successfully implemented for different components of different alloys, and we can see a number of them here, not a complete list, but a fairly extensive one of different components which have been successfully rejuvenated and service life extended. You can see another case study of a 7EA bucket, which was rejuvenated 3 times. Again, this is somewhat dated. Since that time, I believe this set has actually gone through a 4th cycle. But you can see over time, we're getting actual measurable reduction in strength with service, and then successful reestablishment of the properties with each rejuvenation cycle. So here we see the first rejuvenation and the properties that came out of that, going back into service with a drop in strength, and then it's fairly repeatable in terms of the strength drop that we see, and then the restoration of that strength over time. So this part would have been retired at 48,000 hours. It has now exceeded 100,000 hours. And just to put this into dollar terms, just the avoiding of new part replacement costs allowed this operator to save just under $1 million per set. So just to summarize, rejuvenation is something that's been qualified and put into practice. It's really well proven at this point. It's got a over 25-year track record and 0 incidents as a result of these programs. And just to put it into dollar terms, it saved lots of expense by avoiding new part replacement costs. Okay, so that's it for the presentation. I think we'll move into questions if there are any. Just going to stop my share here. Okay, I think we're back here. So I see one question. Do you do full rejuvenation during HIP or before? So typically the hipping is done initially, and then rejuvenation is done. The rejuvenation heat treatments are done afterwards. But part of the reason for that is that we need to combine some of the different temperature cycles into the different repair operations that we're doing, and so it works out more favorably to do it in that order. So I see a question about high entropy
I
alloys.
think it's also easy.
Oh, sorry. Yeah, go ahead, Doug.
I was just going to say it's also a lot easier to hip the alloy when it's in a relatively soft state coming out of service, as opposed to in a hardened state. So hipping is done earlier in the process.
Mm-hmm. So I see another question. Have you experience with solar gas turbines? Yes, we have experience repairing solar gas turbine components. Solar tends to have, I guess, more capture on that market generally, and so aftermarket providers are not as involved with those engines as they are, say, with some of the other OEMs, I would say, as a generalization. But the alloys are conventional, and so rejuvenation is something that's highly applicable to their fleet of engines as well.
I guess we should keep in mind that rejuvenation is alloy specific, not shape of the blade specific. And different manufacturers may use the same alloy, which means that the same FSR rejuvenation recipe, if you want to call it that, will work regardless of the size and shape of the blade or vane component.
Mm-hmm. So I see a question about standards for requalification. Yeah, so oftentimes stress rupture testing is used to ensure that property recovery has been achieved. We regularly include material from the production set that we're rejuvenating to use for that requalification. Microstructural analysis is another thing that is used to ensure that the material has been restored. And then one of the key QA components of a rejuvenation program is to ensure that heat treatment and HIP cycles are as they were intended in terms of temperatures and times and pressures. And so control and review of those parameters are key to the successful execution of rejuvenation. So dimensional changes are mentioned. So you can get minor distortions through stress relief that happen through heat treatment, which also occur with conventional heat treatments as well. I wouldn't say that rejuvenation has a a significant difference in that respect when we're looking at the way other heat treatments impact the dimensions. And so it's something that needs to be looked at. And of course, when we're restoring key dimensional features, like say shrouds on interlocking turbine blades, it's important to order heat treatments such that you're relieving these stresses that might lead to distortion before you're reestablishing those critical dimensions through welding and machining. And so that's an important consideration, but it's not something that typically holds back the successful application of rejuvenation. Distortion of parts is something that happens in service, of course, as well, and that can limit parts reuse, not so much from a restoration of the material standpoint, but rather whether or not the parts can be restored dimensionally. So applying rejuvenation more frequently can, I guess, have a positive impact in that regard, in that if you're regularly reestablishing the strength of the material, then you can keep deformation at bay longer. Another question, do you remove the coating and reapply it after rejuvenation? That's a good question. So pretty much, well, I can say all coatings are not able to go through the rejuvenation cycle. The temperatures that we go to are to a point where coatings can become damaged by that. And so yes, removal and reapplication of coatings is key for rejuvenating components. And so that's both internal and external coatings that are applied to parts. So another question we have is, FSR will be applied to all cases, or there are partial rejuvenation based in the microstructural condition as arrived to the shop? Oh, that's a good question. Yeah, so we don't apply rejuvenation in all cases. There are instances where a part has undergone an extensive degradation that does not necessitate rejuvenation, and so it is only applied at certain intervals. So there are some components where we will do a conventional repair followed by a rejuvenation repair. In some cases, we apply rejuvenation every time because the part is more limited in terms of its overall life. And so it really depends on the component. And the way we make these decisions, we try to take an evidence-based approach to that, to actually look at the components themselves and see what degradation they have, rather than just applying hours-based criteria, which is not specific to how an engine is being run. If an engine is being run hot, it might need a more frequent rejuvenation schedule. If it's under partial load, it might be that the rejuvenation can be spread out a lot more, and so costs can be optimized for a given operation. The cost can be minimized, I should say, for a given operation if we actually take that condition-based approach to applying rejuvenation. Okay, another question. When it comes to the rejuvenation temperature, how much different is there between solid solution alloys compared to precipitation? Oh, okay. Yeah, so that's a good question. So so we're talking about different types of alloys here, components that are precipitation strengthened versus those that are solid solution strengthened. For the vast majority of turbine blades in this day and age, everything is in the precipitation strengthened category. So rejuvenation is always involving solution and aging. There are components that are repaired in the hot section that are solid solution strengthened, and so they might have heat treatments used for stress relief, for coating diffusion, other aspects of the repair, but they don't respond to rejuvenation in the same way that precipitation strengthened alloys do. Has the FSR been used on Rene N5? I assume that's Rene N5 9FA first stage buckets. So we have done demonstrations of that, but haven't actually applied it in practice yet. So single crystals are an interesting category of alloys that you've raised here. So we've done a lot of work on how single crystal alloys respond to rejuvenation. One of the unique aspects of that alloy group is that if there is a combination of cold work in the material and the heat treatment that is applied for rejuvenation, you can actually get something called recrystallization, where new crystals form within the alloy. And of course, a single crystal is designed to only have a single crystal, as the name suggests. And so this can have a detrimental effect on the mechanical properties of these alloys. So with single crystals, there's a unique consideration that needs to be taken. And fortunately, the recrystallization effect is something that can be inspected for. But it's the ability to apply rejuvenation to single crystals all depends on what the cold work history of the component is. And so set to set, there can be variation in how successful rejuvenation is on single crystal alloys alone. For all other alloys, conventional castings, directionally solidified castings, these are not concerns. But for single crystals, that's it's a limitation that that exists, but it doesn't preclude the application of rejuvenation. But it's just something that can lead to some fallout in the process. But if a set of parts has gotten to the point where they need rejuvenation and they're otherwise scrap, it's still worthwhile to attempt rejuvenation. But one has to be aware that that is a possible outcome of rejuvenating those types of materials. So another question. Great questions, everybody. By the way, this is great. After each FSR step during the whole life, the mechanical and metallurgy properties do not change. Do you claim that even 100,000 hour exposure, the total microstructure and mechanical properties rejuvenated completely? Yeah, so we've not seen any limitation with respect to how many times an alloy can be restored in terms of the mechanical properties. And so all of these phase changes can be restored. There's no limitation. But again, with extending the life of parts, other factors can come into play with respect to whether or not parts can continue to operate. So, each time you repair, you thin the component down a little bit, and over time, that can eventually lead to component retirement. Parts can get impact damage, cracking, other. They might have excessive oxidation or corrosion. So there's other things that can limit how much a part can be extended in terms of its life. But rejuvenation, we haven't seen a limitation to how many times it can be applied. Another question, does every FSR recipe include the HIP step? Good question. Yeah, that is not, HIP is not applied in all cases. So there's certain alloys, certain conditions which are favorable to cavitation. And so in some cases it's not included for convenience sake. But there are also some cases where there's some uncertainty with that in that respect, and so it might just be applied in order to just ensure that one has the best possible outcome. So if we can establish the need, then it can be applied on a case-by-case basis, the HIP that is. But in a lot of cases where we just don't have enough information about, how the part's going to be run when it goes back into service or that sort of thing, then it can be applied as a safety measure. Another question, can rejuvenation affect the structure of the whole alloy negatively when it comes to directionally solidified alloys or single crystals? So yeah, I talked a bit about the single crystal limitation. It can be applied, but the extent to which it's going to be successful is going to be a function of the cold work history of that material, whether it's been subject to impact damage, whether it was, whether areas were peened at manufacture, these types of things. With directionally solidified alloys, we don't have that same concern. The DS alloys are intended to have grain boundaries. They have grain boundary strengtheners, and so if there's a limited amount of recrystallization on the surfaces of the parts, then that's a tolerable state for those alloys. If it's more extensive, then it can be an issue, but we haven't encountered that as of yet. So so for DS alloys, it's not really a limitation. For single crystals, there is that some limits there. So another question, FSR process-wise, is there a larger difference between handling DS and single crystal alloys? Based on your experience, which renders better results? So one of the process differences that is important is identification of recrystallization when it comes to particularly the single crystal alloys. So, and also the other thing is that you need to, if you are going to be rejuvenating those single crystal alloys, because I mentioned that you have to actually have two components to have recrystallization. You need cold work and you need the high temperature heat treatment. So cold work is something that we need to avoid in the repair process in order to ensure that we minimize recrystallization. So in some cases, we're not so concerned about cold work. For conventional alloys, we might grip blast them with relatively coarse media to clean them and prep them for various repair operations. But if you're rejuvenating them with single crystals, then that's something that needs to be avoided and can. So you can order the operations in order to avoid that. But it's something that requires a special considerations in terms of how the repair is laid out, and also what inspection steps you need to include in order to make sure that you don't have issues. With DS alloys, it's not so impactful on the way that the repair operations happen. So do you have any experience applying FSR with 7F.04 HPT blades? No. So I do believe the .04 is an N5 base material on that particular component, if I recall correctly. So we haven't gotten to that point yet. Part of it is reaching the age of maturity of the fleet, where it's actually gotten to the point where parts are still repairable from all those other aspects we talked about, but also needing rejuvenation to continue on. And so we're kind of at the cusp of applying rejuvenation to a lot of single crystal alloys at the moment, where a lot of different fleets with modern components like single crystals are starting to get to that point where rejuvenation is necessary. And so I would say that in the next few years, we're going to start seeing a lot more of that. But right now, we've just gotten our ducks in a row in terms of developing those processes, those rejuvenation schedules for the single crystal alloys, and done a lot of testing. We've written a number of papers on the effects of rejuvenating single crystals, and so we can share those if you reach out to us on that. Yeah, so a lot of groundwork has been laid, and now we're probably going to get into that in the near future, but haven't had much practical experience other than a couple sets at this time. As you might know, we usually face some shrinkage during the aging cycle of some alloys, such as IN 901 and 718. Is the case when we perform rejuvenation as well? If yes, how can it be controlled? So if I think if the question is with regards to volume changes with precipitation, that's something that can be a key issue when it comes to uh, stresses developing on welding and post-weld heat treating, that sort of thing. Then yeah, rejuvenation is going to have the same issues that you have when you age alloys, particularly after welding. I mean, when you weld, you're kind of going through a rejuvenation of sorts in the heat affected zone. You're getting hot enough that you're fully dissolving the precipitates, and then with subsequent heat treating, you're going to reform them. And so there's not much difference there than what in those zones around welds and that sort of thing that you would get with a conventional repair. But yeah, similar issues, if you're having those, are going to be applicable to rejuvenation as they would with conventional repairs. Do all FSR process consider a stress test and microstructure test? Any NDT to confirm FSR is well applied. Okay. Yeah, so routinely it's a mechanical test of material that's been processed with the set, stress rupture testing specifically, because we are concerned about, in particular, the high temperature strength of the material. And so that is a routine check. And microstructure is another one that's done to ensure that the microstructure has been restored. And those get applied with each set on material that is processed with the set of parts that are being repaired. So yes. Oh, sorry. And just going back to the last part, the NDT, to confirm that rejuvenation has been successful. We don't apply non-destructive testing to validate that the material has been restored, because we do have material that we can process with the set, and that tends to, there are some NDT methods that can by proxy determine whether or not FSR has been successful, but the more direct measurement of that is with material that's destructively tested. So that's what we tend to do for qualification. You published that you can rejuvenate the CT1 blade of the SGT 400. This blade has internal cooling coating. I want to know that before FSR, you strip the internal coating or not. You know this process is quite hard because it might damage the blade. Yes, that is a consideration. And actually, yes, so for all components that are internally coated, coatings get removed prior to rejuvenation and then need to be reapplied afterwards. And so that's a particular consideration for those types of components. Off the top of my head, I don't actually recall that particular blade being internally coated. I wonder if there's different variants of it out there. My recollection is that. Oh, sorry. You're saying the SGT 400. I was thinking the 100. So our published paper was on the SGT 100, what was previously called the Typhoon blade. And so the SGT 400, which I think was the Cyclone, that is internally coated and has has that concern. But yeah, our paper was on a blade, I think, that did not have an internal coating on it, which is maybe why there's a discrepancy there. Next question. I believe for blade mechanical damage repairs, you perform additive manufacturing or laser deposition. Do you use the same FSR cycle for the post-weld heat treat after the mechanical repair? Yes. So additive repairs for blade tip restorations, shroud repairs on to restore shroud interlocks. Those are all common in repairs. Most FSR repairs that we do have some kind of weld restoration that's happening, and so whether or not the heat treatments have to be incorporated within that in terms of the post-weld heat treatment requirements that are needed. One thing to consider is that when you have a heat affected zone around a weld, it's undergone a thermal cycle that's solutioned it, and so post-weld heat treating is important to reestablish the properties around the zone of the weld, and so that's a important consideration in terms of how we lay out the various steps in the process. I think during FSR process, the formation of incipient melting zone can be probable. Could you please explain how to prevent this deleterious phenomenon? Yeah, that's a good question. So there are alloys where the window between solution and the point in which you get incipient melting is quite narrow. And so developing rejuvenation is about trying to establish those windows and staying within them. And so to this point, we haven't had a problem being able to do that within the temperature tolerances that we're working with. I could conceive a scenario where there is an alloy where that window is too tight, or perhaps even non-existent. It might be that you can't actually fully solution something without hitting incipient melting, but so far we haven't encountered that issue. And so it's a good question. It could be theoretically a limitation for some alloys. Okay. Yeah, really great questions, everybody. This has been a really great discussion.
Kevin, I think there was one question earlier on, which is kind of an interesting one. And I can't remember who asked it, but it was I applied it to high entropy alloys. And personally, I've not seen high entropy alloys in the turbine yet. So I think the short answer is no, but have you any other viewpoint?
No, I don't. Yeah, it's kind of a burgeoning area, and where the applications might exist in hot sections is still something to be explored. So yeah, it'll be an interesting consideration once we get there. But I think we're probably a fair ways off because it's still sort of the alloys are still finding applications in the in these areas. Yeah, so I think we've run through the questions. I guess I'll just kind of, just summarize that it's it's something that's fairly straightforward in terms of what of what it is. It's about developing these heat treatments for different alloys, making sure that we're taking other considerations into account. And yeah, it's been a very successful way for extending component life over pretty much the life of Liburdi. So lots of experience to draw on. We've written a lot of papers on it over the years, and so if anybody's interested in getting more background, then we can we can certainly share some of those with you. And if anybody wants to go deeper on any of these things, and of course, yeah, reach out to us at any time for questions, and yeah, whether or not you've got any particular issues that you'd like to have another look at as well. I think we got a question there about
everybody for tuning in, and thank you, Kevin, for your effort. There is a question there that involves part numbers, and maybe that's best handled by our commercial team.
Bob's got that one.
But again, Kevin, thank you so much for your time, effort to go through these questions. We really appreciate it.
Yeah, thanks everyone.
Roman,
it was a real pleasure.
Send your an email to us. Thank you.
Thanks everybody. I really appreciate it. It was a lot of fun.
Thanks, guys.